Hey everyone, in this video I'm going to talk about spherical mirrors and lenses just a little bit. The lenses I will kind of come to at the end, but I'll also post a video with some examples. Uh, so at this point, we're in chapter 34. We're talking about light as a ray, right? As I described in a previous lecture, we're looking at objects which are big compared to the wavelength of the light, so we can think of it as a ray. And so when light reflects, it bounces off at the same angle as the incident angle. That's the law of reflection. We also talked about refraction. Those are kind of underlying everything, but we're going to kind of look at the images formed by mirrors and lenses based on what happens to those rays. So let me share the screen here. And so let me actually do the slideshow here. So when we look at mirrors, there's actually, we're going to spend a lot of time on spherical mirrors. But before we get to the spherical mirrors, let's talk about a plane mirror. So a plane mirror is just a flat mirror like you have in your bathroom, for example. The idea here is that when we see the image, when we look into the mirror, so our eye is back here, and we're going to see the rays that have reflected off of the mirror from the object down here. And if we look at these rays, each ray that hits the mirror has to obey the law of reflection, right? So incident angle is equal to reflected angle. So this ray coming from the top of the object bounces off the mirror and comes into the eye. Now, what your brain does is it does, again, not know that that ray came from the object and was reflected. It automatically assumes it was traveling always in a straight line. And so your brain extrapolates that ray back through the mirror to the top of the image, and it appears behind the mirror. Now, this is what we call a virtual image because there's no actual light in this area, right? No light actually passes through the image behind the mirror. And so you could not project this on a screen, for example. But that's where our brain sees it. So it actually looks to be behind the mirror at the same distance behind the mirror as it is as the object is in front of the mirror. All right, so we've got some basic things here. We've got an object and an image, and we're always going to look at those two things, and we're going to measure the distances always from the mirror, from the center of the mirror, and we're going to look at spherically curved mirrors. But those are always two numbers we're going to possibly need to know: object distance and image distance from the mirror. Again, in the case of a plane mirror, those distances turn out to be equal. And it won't always be the case for spherical mirrors. This virtual image, also notice, is upright. So it's standing in the same upward orientation compared to the object. We could have images that are inverted, where it's flipped over. We could also have what are called real images, where the image is actually on the same side as all of the light. So it would be over here if we had a real image. And so we're going to see some examples of that with the spherical mirrors. So let's go to the spherical mirrors, and this, let me actually go ahead and look. In this view, it might be a little bit easier to see. So what I'd like, let's actually go back here. We'll do this. So we have the plane mirror at the top here, and you can kind of see the rays reflecting. And then now in this case, our eye would be over here where the rays are coming to, right? And so we see all of these rays coming from the top of the object, and our brain extrapolates them back behind to here. In the case of a spherical mirror, we can have a similar situation, except when our brain extrapolates these rays, they appear at a different place. And so the image now is bigger. It could also be smaller, as in the next situation. But that's what our brain is always doing, is it's extrapolating those rays back in a straight line. And another thing that we'll notice here, we've got P, that's the object distance. from the center of the mirror. I is the image distance, and R is sometimes called the radius of curvature. So it's going to be, if you made this mirror into a total sphere, it would be what its radius is. It turns out, as we will see in the next slide, that there's something else called the focal point. The focal point is 1/2 the radius of curvature. Mainly with this slide, what I wanted to show is that you can obtain images that are slightly different from the plane mirror, but you're really doing the same thing. It's just these rays will bounce off in different directions because the mirror is curved. And so the incident angle is different depending on where that ray hits the mirror. So let's look at the focal point. If you want to find the focus or the focal point of a mirror, you look at a ray that is coming in parallel to the central axis of the mirror. And any parallel ray will reflect off the mirror and go through the focal point for a concave mirror, right? So a concave mirror bends the light toward the focal point. And sometimes when we do the mathematics, we say it has a positive focal point. But you can see these parallel rays come through the focal point. And if we do some calculations using the law of reflection, it turns out that this radius of curvature, or the focal point, is 1/2 the radius of curvature. Now let's look at the other type of mirror. It's convex. It bends outward. And so now when the parallel ray comes in, it's going to reflect out, away from the focal point. So you could say this focal point is a virtual focal point. We're going to denote anything that is virtual by a negative sign when we start plugging in numbers. So we'll see that here in a bit. But you can see the rays do not converge over here. We could never get a real image because the light is not going to focus on one point after it's been reflected. But this is the basic idea of how to get the focal point. Now, one of the things that we will have to do is try to figure out where is the image. And this is to do this, we do something that's called ray tracing, or making a ray diagram. And we need at least a couple of rays to do this. So let's look here on the left side. And this is going to be for our converging spherical mirror, or concave, right? It converges the light to the focal point. So we can start with our parallel ray. It's going to come from the top of the object, hit the mirror, and then go through the focal point. So we know that the image has to lie somewhere along this reflected ray. We need another ray to determine where that second reflection crosses, and that will tell us where the top of the image is. So why don't we do the reverse of this ray? We are going to go ahead and look now in the second ray. We're going to add ray 2. It's going to go through the focal point. So we're kind of just going backwards from the first ray. If it goes through the focal point, it will hit the mirror and come out parallel. Now you can see right away where the image is going to be. It's going to be, the top of the image is going to be right where those two reflections cross. And you can draw that image just as an upside down arrow with its top at the crossing point. Now the foot of the image has to be along the central axis, right? Because any ray coming from the foot is going to hit the flat part of the center of the mirror and just reflect straight back. So we can see that our image is just upside down. So I say it's an inverted image. Now this particular image is a real image because the light is actually passing through the image. Now we could draw a third ray, and our third ray basically is going to just go straight through the top of the image, hit the mirror. It's coming along a radial line here, so it's just going to reflect straight back. And so you can see this third ray. But you really only need the first two rays to draw the image. Okay. We will see in the problem example I'm going to do that you don't always get a real image for the converging mirror. In fact, if you put the object inside the focal point, you will get a virtual image. And we'll see that in the example that I have. But let's look at our other type of mirror, for which we always get a virtual mirror or virtual image because the light is spread out. It's never going to cross on the real side. So let's go ahead and take a look at this second one. I can again start with my parallel ray, and it's going to come in parallel, but now it reflects away from the focal point. So I'm going to extend the straight line back through the focal point here. Now, the next one, ray 2, is going to come toward the focal point, exactly like here, but it doesn't actually go through it because it's on the other side of the mirror. It's headed toward the focal point, and then it reflects straight back. Now, if I extend that second ray, it comes parallel through, and you can see now the crossing point is right there. And so I draw my image where those points cross. Now, this is a virtual image because the light does not actually go behind the mirror, but my brain is extrapolating those rays backwards to see that it comes from that point. We could draw a third ray just going straight toward the center of curvature and bouncing straight back again, and then extending it through. And you see all those rays cross at the top of where the image is. Okay, so this is the basic idea of ray diagram. It's a little tricky. It takes some practice to get used to. So you might even try just drawing several of them. Make up several situations. Draw a mirror, put the object at some distance, make a certain focal point, and practice drawing those. In the book, there are several diagrams of all the types that you could have. So you can always take a look and check yourself with the book, or if you had questions, you could ask me. We are now at the point where we need some equations because we don't want to just draw diagrams to determine or solve problems. We need some numbers, right? Some equations. And not going to derive these equations. I just want to describe them. The derivations are kind of long, and they are at the end of the chapter in the textbook if you're interested, but we're going to try to just apply them. So now remember, going back, we're going to call our object and image distances P and I. Sometimes you'll see, again, different notations. You might see D sub O for object distance, D sub I for image, but we're going to stick with what the book does. And I'm going to write down our first equation, which relates the P object distance, or object distance, I image distance, and focal distance. So it's 1 over P plus 1 over I equals 1 over F. Now I need to be careful because their negative signs are going to distinguish between whether things are virtual or not. So if I have a converging mirror, right, this would be the concave mirror, focal length is positive. If I have a concave or diverging mirror, F is negative because it's on the negative or on the virtual side. So just go back real quick. You can see that again in this over here, this type of mirror, this diverging or convex, has a negative focal point because anything on the virtual side where the light does not go is going to be denoted by a negative number. All right, so we can use this equation to solve problems. For example, if we happen to know the focal length of the mirror and we know where I put the object, P, I know what my P object distance is, which will generally always be positive because it's on the real side, I could solve for I. Okay, now a second equation that you'll see in the problems is magnification. Now magnification is the ratio of the image height to the object height. So basically we're going to call it M is the height of the image over the height of the object. So again, going back here, I might look and I would see, for example, in this situation, this is my H object, and this is my HI. Now, one thing to note, right, when it's a real image, it's flipped over, it's inverted. And we got to be a little careful because we want to call that a negative magnification. If the object is inverted, it's a negative magnification. If it's upright, M is positive. Now we have one other problem because it turns out that if you work through all the equations, that the ratio is I over P. So the height of the image to the height of the object is the same as the image distance to the object distance, but I need to put a negative sign in front. Now the reason for that is I is negative for virtual images, whereas it is positive for real images. So one thing you'll see in the previous picture here, when I have my virtual image, it's a negative image distance, a negative I, but it's upright, so it's got to be a positive magnification. That's why I have this negative sign here. Because when I plug in my negative virtual image distance, it will cancel and make the magnification positive as it should be. All right, so that's a pretty quick description. Hopefully it will get you started with the problems. And I'm going to do one example, and then I'll post some other examples, maybe with both mirrors and lenses. But let's do an example here. So this is a problem from the book. In this case, we have a concave shaving mirror. So this is what I would call a converging mirror, right? It's going to look like this, and I'm going to have my object somewhere over here. Now, it says that the image is upright. Now, I have to guess that it's going to be a virtual image because we don't have all of our images that are upright are virtual. The real images get flipped over upon the reflection. And it's also much bigger. It's 2.5 times. So it's going to be over here somewhere. I don't know exactly what my P and I are yet, but I can figure both of those out, right? From the fact that the magnification is negative I over P. And from my mirror equation, 1 over P plus 1 over I is equal to 1 over F. I'm going to have to combine these equations. Now I know that M is 2.5, so I can solve for I. It's just negative 2.5 P. Then what I'm going to do is plug this in to this equation to give me 1 over P plus 1 over negative 2.5 P is equal to 1 over F. Now I should be able to solve this in terms of the focal length, right? And to do that, I could write this as 1 over P plus, or actually negative. You could write it as minus, right? But it's going to be 2/5 because, so this is 2.5 is 5 halves. Flip that over, it's 2 over 5 P. And I can now get a common denominator, just multiply by 5 over 5 on that. And this becomes 3 over 5 P is equal to 1 over F. So basically just combining and solving the equations, I find that my object distance is 3/5 the focal distance. Now, it makes sense going back to my images that I had, because if you look at my case here for my converging mirror, the object is outside the focal point and I get a real image there. But in this case, I'm going to be closer than the focal point, and we'll see that we get a virtual image. But let's go ahead and get the number, because we are also told that the radius of curvature is 35 centimeters. From that, we can get the focal distance because it's half that radius of curvature. So it's 17.5 centimeters. So plugging this in here, I get a distance of 10.5 centimeters. And that is how far the mirror is from the face, because the face is the object, right? And so the image is going to supposedly appear behind the mirror, virtual, and be 2.5 times larger and upright. Okay, and that's because I have a positive magnification that it's upright. I have a negative image distance, as you can see from the negative here, because it's virtual. And then I end up with my positive object distance. But let's try to draw the ray diagram if we can. So I'm going to draw my central axis and my mirror. Now my focal point is maybe out here. Whoop. Let's draw it there. And my object is somewhere in here. Okay. So let's draw our first ray, which is the parallel one. It's going to come in parallel and then reflect. And again, it's hard for me to draw straight lines here, but it's going to reflect out that way. Now, I have a little bit of a problem here because if I want to draw the next ray, it's a little different than the previous diagrams. What I can do is draw a ray that's coming from the focal point, right? It's coming from the direction of the focal point here. And it's going to hit the mirror like that. But since it's coming from the focal point, it's just the opposite of the first ray. It's going to go out parallel. Now, again, I'm looking on the left side of the mirror here, and so I'm going to extend these reflected rays back. And again, my drawing's not great, but you can see that they're going to cross back here, and my image is going to be upright, virtual, and it's going to be bigger than the object. Now, to get it exactly perfect, I'd have to measure everything and put it to scale. But hopefully you get the basic idea. So again, these are the two equations you can use to solve the problems, and you may also be asked to draw these ray diagrams, so it's good to practice those. I will post other videos from YouTube that have problem examples with these. Last thing I want to mention, I'm not going to go into detail right now, but the exact same thing happens for what are called thin lenses. So for a thin lens, we have basically two types again, diverging and converging. But now the ray is not reflected, it's refracted through the lens. And so for example, let's look at our converging case when we're outside the focal length. Now, the ray is going to go through, but a parallel ray will go through the lens and bend through the focal point. A ray that goes through the focal point first will come out parallel, and then a ray that goes right through the center of the mirror or the lens just goes straight through. So we can see that in this case, we get a real object, right? Because now the real side has flipped because the light actually passes to the opposite side of the mirror. And in fact, when you are looking, you're now not looking on the left side, you're looking through the lens. You're holding the lens, looking through, and the object is over here. So this is my real side. And if you go back to the mirror images, you see this is the exact same ray diagram as this one. I've got my parallel ray through the focal point, and then my ray through the focal point coming back parallel. It's exactly the same, just kind of folded over, right? Because now our virtual and real sides have flipped. So what if we bring the object inside the focal point for the converging lens? Well, we should expect, similar to the converging mirror, to get a virtual image. And this is what happens in image B here. The parallel ray, right? So if my object is right here now, my parallel ray goes through the focal point. I could draw my ray going to the center, but if I extend those two back, they cross over here at the top of the image. Now my other ray could be from the focal point going out parallel. These will take practice, and it's good to look in the book and see the examples that they show there. Lastly, we have our diverging lens. And so in the case of a diverging lens, a parallel ray will diverge away from the focal point. So now this is a negative focal point because it's on the virtual side. And we could also draw a second ray that's headed toward the focal point on this side, and it's coming out parallel. Lastly, we could draw a ray straight through the center. And again, remember, your eye is on the right side, so you're looking through, and your brain is going to see all these diverging rays, and it's going to extrapolate them straight back to where they cross, which is right here at the top of the image. Okay, so hopefully that gives a quick rundown on lenses and mirrors and the ray diagrams. Again, I'm going to try to post some videos from YouTube. Maybe that they're not not ones I've created, but they do examples of these problems.